Hey everyone, and welcome back to the channel. Remember last time we dove deep into the world of motion in a straight line. We unpacked concepts like displacement, velocity, and acceleration, and even saw how those relate to some really neat equations. Well, buckle up because today we are going to level things up. Today we are breaking free from the single straight path and venturing into the fascinating realm of motion in a plane. Now, before we launch into this two-dimensional adventure, let's do a super quick pit stop to jog our memory about what we learned in one dimension. Remember, in one dimension, we described an object's position with a single number along a line. Its velocity was how that number changed over time, and acceleration was how that velocity changed. We even had those handy equations of motion that linked these quantities together when the acceleration was constant. Keep those ideas in the back of your mind because the core principles are going to be our trusty sidekicks as we explore this new dimension. Alright, so what exactly is motion in a 2D plane? Well, instead of just moving forward or backward along a straight line, now our objects are free to roam on a surface, like a piece of paper or the screen you are watching this on. This means to describe their position, and we now two coordinates, usually an x and a y. Think about it, a fly buzzing around a room, a ball thrown across a field, or even a car turning a corner. All examples of motion happening in two dimensions. And because we are now dealing with directions in a plane, our good friends vectors are going to be absolutely crucial. Remember, vectors have both magnitude and direction. In two-dimensional motion, the displacement, velocity, and acceleration all are vector quantities, each with an x and y component. The beauty is we can often analyze the motion in the x and y directions independently. This independence is a game changer, and it brings us to one of the most classic and fascinating examples of 2D motion. Projectile motion. Have you ever thrown a ball or watched a fountain? These are perfect examples of projectiles in a motion. A projectile is any object that is launched or thrown and then moves freely under the influence of gravity alone, neglecting air resistance. Now, here is where our vector knowledge and independence of motion in x and y really shine. When we launch a projectile at an angle, its initial velocity has both a horizontal component and a vertical. Here is the cool part. If we ignore air resistance, there is no horizontal acceleration acting on the projectile. Its horizontal velocity v of x remains constant throughout its flight. However, in the vertical direction, gravity is constantly pulling downwards, causing a constant downward acceleration. Our good old g, approximately 9.8 meter per second square, near the Earth's surface. This vertical acceleration, Ay equals to minus g, is what causes the projectile to curve downwards, resulting in that beautiful parabolic path. So, to analyze projectile motion, we essentially treat it as two independent one-dimensional motion problems simultaneously. The horizontal motion is essentially constant because Ax equals to 0. Hence, we can use the simple equation x equals to x naught plus v naught xt. And for the vertical motion, a constant acceleration Ay equals to minus g keeps acting. We can use our familiar 1D equations of motion. Just remember, we are dealing with the y direction. By combining these independent analyses, we can figure out all sorts of things about the projectile's flight, like its maximum height, its range, and its time of flight. Now let's take our analysis a step further and derive some useful equations for projectile launch from a certain height y naught and landing at the same height y equals to y naught. This gives us some powerful tools to quickly analyze scenarios like a ball thrown from a cliff landing at the base if we consider the launch and landing heights relative to a chosen 0 point. Let's start with our vertical motion equation. Y equals to y naught plus uyt plus half at squared. Since we are considering the case where the final height y is equal to the initial height y naught, we can set y equals to y naught. Hence, y naught equals to y naught plus uyt plus half minus gt squared. By simplifying the equation, we get 0 equals to uyt minus half gt squared, and factoring out the t, we get t times uy minus half gt equals to 0. And then t equals to 2uy by g. Substituting uy equals to u sine theta to get the time of flight in terms of initial velocity and launch angle, we get t equals to 2u sine theta by g. Now moving to the horizontal motion equation, x equals to x naught plus ux times t. Assuming the launch point is x naught equals to 0, the horizontal range r is given by r equals to uxt. By substituting ux equals to u cos theta and the expression for t we found earlier, we get r equals to u cos theta times 2u sin theta by g. By using the trigonometric identity 2 sin theta cos theta equals to sin 2 theta to simplify the range equation, we get r equals to u squared 2 sin theta by g. Now finally deriving the equation for the maximum height h. At maximum height h, vy equals to 0. By using the equation vy square equals to uy square plus 2ay y minus y naught, where y minus y naught equals to h, we get 0 equals to u sine theta whole square plus 2 minus gh. By solving for h, we get h equals to u square sine square theta by 2g. So now we have these handy formulas for the time of flight, horizontal range, and the maximum height of a projectile launched and landing at the same vertical level. These can save us some steps in certain types of problem. Alright, now with these new tools in our arsenal, let's put our knowledge to the test with a couple of problems. Grab your thinking caps. The first problem. A ball is kicked from the ground with an initial velocity of u equals to 25 meter per second at an angle of theta equals to 45 degree above the horizontal. Assuming it lands back on the ground, calculate its horizontal range. Okay, so now to solve this problem, first we need to identify the given values. We are provided with the initial velocity, which is 25 meter per second, and the angle theta. We can use the range equation to solve this problem. R equals to u square sine 2 theta by g. We can substitute in the values and get 625 meter per second squared times sine 90 by 9.8, which is equals to 625 meter per second squared by 9.8, which is roughly equals to 633.78 meters. See how our derived equation made that calculation a bit quicker for this specific scenario, where the launch and landing heights are the same. So we have continued our journey into the 2D world of motion, focusing specifically on projectile motion. We saw how to analyze it by breaking it down into different independent horizontal and vertical components, and even derived some useful equations for specific scenarios. I hope this video has further solidified your understanding of motion in a plane. If you found it insightful, don't forget to hit that like button and subscribe for more physics explorations. In our next video, we'll be tackling circular motion. Thanks for watching, and I'll catch you in the next one. Keep those physics concepts flying.